Okay, hello everyone. Welcome to part 2 of our topic in fluid properties. Last video, we talked about the properties involving mass and weight. We had mass density, or simply the density, the specific weight, and the specific gravity. We also talked about the ideal gas law. In addition, we also have properties involving thermal energy. For a specific heat, it is the capacity of a substance to store thermal energy. It can be denoted by Cp or Cv. At constant volume, we use Cv. At constant pressure, we use Cp. For air, the Cp is 1 kJ per kilogram Kelvin. The ratio of Cp to Cv is equal to K, or the heat capacity ratio. For air, this is 1.4. In theory, specific heat is the amount of thermal energy that must be transferred to a unit mass of substance to raise its temperature by 1 degree. For example, if you want to raise the temperature of air from 1 Celsius to 2 degrees Celsius at constant pressure, you need to add 1 kilojoule per kilogram of thermal energy. Units for specific heat can be kilojoule per kilogram Kelvin or BTU per pound mass Rankine. Next, we have internal energy, or U, or the energy that a substance possesses. Units are kilojoule per kilogram or BTU per pound mass. Lastly, enthalpy H, or the total heat content of a system. Mathematically, enthalpy is the sum of internal energy and the product of pressure and volume, or specific volume rather. Units are the same with internal energy, with kilojoule per kilogram or BTU per pound mass. The main topic for this video is about viscosity. Viscosity, also called dynamic viscosity or absolute viscosity, is a measure of a fluid's resistance to deformation under shear stress. So for example, crude oil, it has a higher resistance to shear than water, meaning crude oil will pour more slowly than water from an identical beaker held at the same angle. Mathematically, viscosity is the ratio of shear stress and velocity gradient. Shear stress, or tau, is the ratio of force over area on a surface when the force is aligned parallel to the area, as shown in the figure. Velocity gradient, or change of velocity with respect to change of distance from the wall y. This is also equal to the rate of strain P, which is the change in an interior angle of a cubical element that was originally at right angle. Later on, we will try to derive this formula. The concept of viscosity is the same with shear modulus from solid mechanics. They are the same because they are both constant of proportionalities. Our task now is to derive the rate of strain. Okay, so consider a wall here with fluid that has a parallel flow. Every fluid element with distance y from the boundary as a corresponding velocity. Initially, we have this rectangular element. Since the top surface has higher velocity than the bottom, this will cause deformation or strain with respect to time, thereby causing an inclination on the sides of the rectangle. So let's take the rectangular element time t with shear force F tau. Let the bottom surface have velocity v and the top surface to have v plus delta v, since it should be faster than the bottom with distance between them equal to delta y. After some time delta t, the rectangular element has moved and been deformed with side inclined at an angle delta phi with respect to vertical. The distance moved by the bottom surface after some time delta t is v multiplied by delta t. The distance moved by the top surface is the quantity v plus delta v times delta t, or it is equal to v delta t plus delta v times delta t. The difference of these two distances is the delta v times delta t. Now, isolating the triangle with interior angle delta phi, we may express the change in angle to be the ratio of change in opposite side over change in adjacent side, wherein the opposite side is the distance delta v times delta t, and the adjacent is the distance between the two layers equal to delta y. Rewriting the derived equation, we get that the rate of strain delta phi over delta t is equal to the ratio delta v over delta y, or it is equal to dv over dy, or velocity gradient is equal to rate of strain. Going back to our fundamental formula for shear stress, tau is equal to viscosity times rate of strain. By substitution, we get tau is equal to viscosity times the velocity gradient. Rewriting the equation again, we get viscosity is equal to shear stress tau divided by the velocity gradient. So known units for viscosity are poise, Dyne second per square centimeter, Newton second per square meter, Pascal second, and pound for second per square foot. Viscosity of water at 20 degrees Celsius is 1 centipoise, or 0.1 poise, or 0.01 Pascal second. We also have kinematic viscosity, which is the ratio of viscosity and density of a fluid. Known units are square meter per second and square foot per second. To relate viscosity with temperature, the viscosity of liquids decreases as the temperature increases, whereas the viscosity of gases increases with increasing temperature. Formula for liquid, we use the formula mu is equal to C e raised to B over T. For gases, we use the Sutherland's equation to estimate. We also have Newtonian versus non-Newtonian fluids. Newtonian fluids are fluids which have shear stress is directly proportional to the rate of strain. So we have a straight line. For non-Newtonian fluids, shear stress may not be directly proportional to the rate of strain. So we have this shear thinning, shear thickening, and Bingham plastic. For shear thinning, the ratio of shear stress to shear strain decreases as the shear strain increases. For shear thickening, the viscosity increases with shear rate. For Bingham plastic, it acts as solid for small values of shear stress and then behaves as fluid at higher shear stress.